All right, guys, here we go. Section 6.3, binomial and geometric distributions. Binomial and geometric random variables. Okay, so this is 6.3. So we're going to talk about what's called a binomial setting. Okay, binomial setting and binomial random variables. Binomial, bi means two, so you want to remember that. Okay? This arises when we perform several independent trials. Independent, which means one does not depend on the other. Okay? Of the same chance process and record the number of times something happens. So there's an acronym. Okay? It's right here. It's called BINS. We're going to use BINS. Okay? It's going to help us. It's going to help us determine if we have a binomial probability distribution, if we have a binomial random variable, if we have a binomial distribution. Okay? B stands for binary, which means there has to be like a success and a fail. There's two things that can happen. It's not like four things that can happen. Either you make the shot or you miss the shot. Either you roll a 5 with a die or you don't roll a 5 with a die. Okay? It has to be a situation where you can talk about a success and a failure. Independent. One trial has to be independent of the other. When you flip a coin, okay, and then you flip a coin again, those events are independent. Whether you get a heads in the first try or a tails in the first try, it doesn't affect your next one. Rolling a die, independent. Technically, shooting a basketball, independent. Okay? Number. They have to tell you how many times you're going to do this ahead of time. It has to be a fixed number of trials. And then S, success. You have to have the same success rate each time. When you flip a coin, the probability of getting heads is 50% each time. When you roll a die, the probability of getting a 5 is 1 out of 6 each time. So that probability needs to be the same. Okay? And here at the end it says there can be more than 2 possible outcomes. They just need to be defined as success and failure. So if you're rolling a die, there's technically 6 things that can come up. But when you define your random variable, you want to define it as the probability of rolling a 5, the probability of not rolling a 5. Okay? Then you can determine that as a success or a failure. All right, so binomial random variable and the binomial distribution. So it says the count x of successes in a binomial setting is a binomial random variable. The probability distribution of x, random variable x, which is a binomial random variable, is a binomial distribution with parameters n and p, where n is the number of trials and p is the probability of success in any one trial. Okay? The possible values of x are the whole numbers from 0 to n. We're going to talk about it. We're going to spend a lot of time on this. Okay, so dice, cards, and hoops. Determine whether the binomial random variables below have a binomial distribution. Justify your answer. All right, well, let's take a look. We've got 2 of them here. Okay, so the first thing I'm going to do is I'm going to write out BINS. B-I-N-S. And I'm going to verify that this is a binomial distribution by checking each of these conditions. So B stands for binary. I'm going to write it out now, just so you guys get used to seeing it. Binary, which means you can determine this situation as a success or a failure. So you're rolling a fair die 10 times and let x equal the number of 6s. Okay, so if they asked you to, provide explanation, which they may with these, they may ask you to provide explanation. You would say, getting a 6 equals success. Okay, and then anything else is a failure. So can we do it by success and failure in this situation? Yes, we can. I, independent. Okay, can I say that they're independent? Yes, rolling a die is independent. Rolls of a die are independent. And do they give us a fixed number of trials at the beginning? Yep, rolling 10 times. So I'd say n equals 10, that checks. And then success, the probability of getting a 6 equals 1 in 6, check. So is this a binomial distribution? Yes. Binomial distribution. Okay, let's do this next one. Do the same thing, we're gonna do bins. So I'm gonna write B, I, N, S. Binary. What are we doing? We're shooting a basketball 20 times from various distances on the court. Let Y equal the number of shots made. So, shots made, shots made, okay? Shots made equals success, okay? And miss is a failure. I, independent. One shot should be independent from the next. One shot, independent from next shot. N, yep, N equals 20. Now, probability of success. In this one, they're talking about doing it in various distances. So if we're shooting from various distances, the probability of success is not the same. If you're shooting a shot near the basket, okay, and you're shooting a shot away from the basket, those probabilities are different. So this one fails, okay? The probabilities are not the same from love the markers. Love this little marker. From various distances. Okay? Make sense? Okay, so those are two. I think there's one more on the next page, if I remember correctly. Let's figure that out. Check my battery space and make sure that I have enough. I know I'm going to run out, okay? I know I'm going to run out here. Well, I think I'm so good. All right, so it says observe the next 100 cars that go by and let C equal color. So let's do B, I, N, S. So 100 cars. Let C equal color. Well, it doesn't give us a binary situation. It doesn't tell us that you're looking for red cars and cars that aren't red, or blue cars and cars that aren't blue. So it's not a binary situation. Not binary. Binary means two. It has to be one thing or the other. And here they're just saying let C equal color. So you could have a bunch of different colors, so it's not two things. All right? So that takes care of those. So what I want you guys to do is I want you to pause the video and I want you to do the CYU on page 385. Okay? I'm actually probably going to end up pausing the video too. But that's what I want you guys to do. Pause the video, do the CYU on page 385, and then why do they call it a CYU? Check your understanding. That's what we're trying to do. We're trying to check your understanding, make sure that the stuff that I just did made sense. Because if you're just sitting there doing the stuff, it's, you know, you're taking notes. Taking notes isn't going to get you where you want to go. Okay, so let's take a look. So for this first one, it says, for each of the following situations, determine whether the given variable has a binomial distribution, which I make that a little clearer. I know you guys can see it in your book at home. Justify your answers. So we can do bins for all of these. Okay, we gotta do bins. So let's do it. First one, BINS. This is number one. Okay, shuffle a deck of cards, turn over the top card, put the card back in the deck, important thing they said there, and shuffle again. Repeat this process 10 times. Let x equal the number of aces you observe. So if x equals the number of aces you observe, then we are going to say success is getting an ace. Failure, anything else? Binary, check. Independent. If you're shuffling a deck of cards and you're pulling off one card, unless you're a card shark like Mr. Fazio over here, with his card tricks, we're going to say that they are independent. Drawing cards from a deck. Is, because you're doing drawing, right? Drawing is independent. And does it tell us a number of things? Yep, n equals 10. Fixed set. And then success. The probability of getting an ace, is 1 in 4. And what makes that 1 in 4 is this key thing that they said. Put the card back in the deck. You're replacing the card. Okay? When you replace that card, the probability of success stays the same every time you're doing it. So number one is a binomial setting. This is a binomial setting. Hope you got it. Number two. Choose 3 students at random from your class. Let y equal the number who are over 6 feet tall. Okay, so let's look. Choose 3 students. All right, so let's do bins. B-I-N-S. Is it binary? Yes. Success is greater than 6 feet. Failure is less than 6 feet. Independent. The way you're choosing the students, I would say that they're going to be independent of one another. Okay, the process is independence. Number, yeah, you're choosing 6. Probability of success. It says you're choosing 3 students at random from your class. So when you choose that first student, okay, the probability of getting someone who's 6 feet or above, let's say it's, I don't know, let's say you have 7 students in your class and, or let's say 25 students in your class and 7 of them are over 6 feet. When you choose that first one, you get a 7 out of 25 chance. Now, when you choose the second one, the probability changes. The probability is not the same. You're not replacing. There's no replacement. So the probabilities of success is not equal. Okay, so this is not binomial. Not binomial. And then we get to number 3. B-I-N-S. Flip a coin. If it's heads, roll a 6-sided die. If it's tails, roll an 8-sided die. Repeat the process 5 times. Let W equal the number of 5s. So is it binary? Success, number of 5s, failure, anything else? Independent, you're rolling a die, flipping a coin. Rolling a die, and flipping a coin are independent events. N, 5 times, Probability of success. I would say that's different, so this fails. Okay? If you have a 6-sided die, you're going to have a 1 in 6. If you have an 8-sided die, okay, it's going to be like 1 in 8. So the probabilities are different, so it's not binomial. Not binomial. Okay? Let me just see if there's anything else that I want to add to that. I think on the second one, it says choose 3 students at random from your class. I think you could also probably question the independence on that one too. Okay, I think the probability of success is going to be different, but I think you can also question whether or not that's going to be an independent event. Okay, and again, it's because it's that you're sampling without replacement. Okay, if you were replacing it, then that would, but the probability of success is different, it's not binomial, but when we think of independent as well, and you choose that first student, that second student that you choose is going to change the probability of the first student. So I think this one's going to fail in 2 places. All right? All right. Moving right along. Good place to stop. How long did we finish? I think that's going to be a good place to stop for the first video today.